Good morning. Here we are once again. It's the physics video lecture. Physics 105A video lecture 13. And we're working on oscillations still, but we're going to take it somewhere else today. So let me just quickly review. It's all been about Newton's law, of course. Newton's law as the force is a function of position, then you could say we're at the point where we're using a linear restoring force. So we've obtained this. There are, of course, a lot of steps in between here. For example, forces that are restoring forces, but not linear forces. But good, we've discussed those things, and we've arrived at this differential equation here. Maybe I'll put a subscript there. So this is a linear differential equation, second order, with constant coefficients. Same thing here, linear, comma, second order differential equation with constant coefficients. And there's a general theory for those that involve the use of complex numbers and functions. And so what we're going to do is a little section on complex numbers. In the course of the semester, we'll probably do quite a bit with that. But for starters, so let me finish this line here. For starters, we're going to just talk about complex numbers and how they're related to this differential equation here. So I add constant coefficients. So next here, I'll just write next complex numbers, and then we'll come back to this equation here once we've discussed the complex numbers a bit. Okay, so here we go. So there are different ways to introduce the whole idea, but let's just go to the solution of the quadratic equation. And suppose we just have all real numbers, real coefficients. We've got ax squared plus bx plus c is equal to 0. Everything's real. In particular, a, b, and c are real. Because that's all we know yet, right? We don't know the complex numbers yet. But we come to discover that we can solve this equation, and the solutions look like this. 1 over 2a negative b plus minus the square root of b squared minus 4ac. And that's nice, so there are two solutions generally to the quadratic equation. But then we learn that we have to deal with this thing here. Okay. B squared minus 4ac has to be positive because otherwise we can't take the square root. So we have b squared minus 4ac must be greater than or equal to 0. And as an example, suppose we have x squared plus x plus 1 is equal to 0. We're trying to solve that, and we use our formula here. We have x equals 1/2 negative 1 plus minus the square root of, well, b squared, 1 squared minus 4, which is what? Minus 3. So we'd like to just be able to write this down and keep going. And it turns out that if you introduce this imaginary quantity, so-called, which is the square root of -1, such that I squared is equal to -1. If you do that, then you can do the following. Now you can say your solutions are -1/2 plus minus I square roots of 3 divided by 2. And this has just been done formally, but if you go back into this equation with these roots, you'll find, sure enough, it works. Okay. So this is kind of an opportunistic thing. You found a scheme with which you can do these things. So this already shows an aspect of here. Here you've got a so-called complex number. It has a real part and it has an imaginary part. Okay. So let's go ahead and take that at face value and then develop what happens. Good, so I'll define, right, at this stage it just works, okay? What I'll do is I'll define the complex numbers now. So complex numbers. So I'll go ahead and let Z be a complex number x plus I times y. So x and y are just real numbers. And about this quantity here, I, we just know that I squared is equal to -1. Square root of -1. Now, it turns out that if you define complex numbers this way, you have addition, subtraction, multiplication, division. You can do all of your arithmetic that you're used to doing. So, addition is defined like this: z1 plus z2 equals x1 plus iy1 plus x2 plus iy2. And what you do is you combine the real parts. So you've got x1 plus x2 plus I times y1 plus y2. As said before, I'll add this to the original definition here. X, referring to z right here. X we call the real part of z. Y we call the imaginary part of z. I'll put that here in words as well. The real part and the imaginary part. So there's addition. Subtraction, of course, is going to be done the same way with a -1. Okay, so subtraction, I'm just going to check off. Same way. How about multiplication? If we're going to multiply these two numbers, we're just going to write z1 plus, or times z2, sorry. z1 times z2 is equal to x1 plus iy1 times x2 plus iy2. So we just have to multiply this out, and we already know to gather the real and imaginary parts together the way we did right here. So we're going to have x1 times x2, that's a 2, x1 times x2, and then y1 times iy2 is going to give us minus y1, y2. So we're going to have x1, x2 minus y1, y2. And then what's common with the i's here is I times y1, x2, and I times x1, y2. So I times x1, y2 plus y1, x2, x2, y1. So there's the multiplication. Okay, it's already not looking so simple as addition was, but we can multiply these. There's the rule. What about division? So we're just doing our arithmetic operations. And we see they kind of get progressively more complicated. Division. We're going to have z1 divided by z2. And now we have our x1 plus iy1, x2 plus iy2. And we're wondering what to do here. But then based on what we just saw up here, what we can do is we can multiply this number here, this quotient, by 1. And we'll do it in such a way that x2 minus iy2 because if you look at the denominator, you're going to get x2 squared. Now I times minus I is plus 1, so you're going to get x2 squared plus y2 squared in the denominator because the cross terms vanish. I y2 x2 and minus I y2 x2. Okay. So we're just getting x2 squared plus y2 squared, which is just a well-defined real number. And then in the numerator, we have to deal with it. So we have x1, x2 plus y1, y2, and then plus I times y1, x2 minus x1, y2. x2 minus x1, y2. Okay, so it's doable. And it's not looking like a lot of fun, right? We don't want to memorize these things just to do some simple quotient here. However, there is help on the way, so to speak. First of all, we realize we can do all the arithmetic we want to, in principle. Next, I'm going to define a couple of things that have come up here. The first thing is the complex conjugate. Complex conjugate. And so if z is equal to x plus iy, then z bar is equal to x minus iy. You're replacing anywhere there's I, you replace it with minus I. And I'll also write or, and you'll see in physics we often use Z star, Z bar on top. I'll probably go to using a star as we progress here, okay? Use the bar right now. So that's your complex conjugate. We used it right here in the denominator. So the complex number times its complex conjugate gave a real number, and this will be reminiscent of something very soon. So we have, and z bar is equal to x squared plus y squared. Okay, talking about that. And we can define the magnitude of z is equal to the square root of x squared plus y squared. And of course, the magnitude squared in complex numbers is z times its complex conjugate. So this is going to be very useful. It allows us to find expressions for the real and imaginary parts in a pretty typical way. Okay, so I'm going to erase this board, but remember the real part was just this, the imaginary part was that right there. In our larger expressions, the real part was this thing divided by that denominator, and the imaginary part was that part in parentheses divided by the same denominator. Okay, so where are we? So now there's an expression using the complex conjugate. So now we have, we can write the following. Given z, the real part of z, for, I'll just write this, x plus I, y in general. The real part of z can be written as z plus z complex conjugate divided by 2, and the imaginary part can be written z minus the complex conjugate of z divided by 2 times I. And you just see that trivially by adding z plus z complex conjugate, and the iy's are going to cancel. So if you add those two, you can have a 2x, and you divide by 2, you're just going to have x. Okay. And if you subtract the complex conjugate from this z, then you're going to have iy minus negative iy, so 2iy, and so you divide that by 2 times I, and you just get y. Okay. So make sure you see these. They're very useful. Okay, but now say we wanted to do operations like squared, cube, square root, cube root, and things like that. It can get hairier and hairier. However, there is a good out to this whole problem, and that is expressing complex numbers in the complex plane. Okay, so now our next topic is the complex plane. I'll just, the set of complex numbers we can do with a C with a line there, we can refer to the complex plane in the same way. So now we've got our X and our Y axis. X and, or we could say the IY axis. And then any of these points, X plus IY, is just some point here in the complex plane. And what's really clear is that the addition as defined earlier just turns out to be the same as the addition of vectors in the plane. Vectors of 2 components in the plane. So here we have an example. We have X, we have Y, or I times Y if you want, is that point right there, and that represents the complex number. The complex conjugate, have I erased that now? Yeah, sorry. The complex number X plus IY, the complex conjugate X minus IY is just mirrored across the X axis. So if this is Z equals X plus IY, then this here is Z complex conjugate equals X minus IY. And what about this Z bar, X squared plus Y squared? Well, now you realize that we're apparently looking at the unit circle, right? Any 2 points here, X squared plus Y squared, you go around all those possible Z bar. For example, if you looked at all of the complex number z whose magnitude is 1, then you'd be looking at the unit circle in the complex plane. So I'll write here, example, z equals 1. That's the set of z such that x squared plus y squared is equal to 1. And of course, that's the unit circle. Draws a unit circle there. That would be an example there. Okay. So once we have the complex plane, we're ready to introduce polar coordinates. Okay. This technique is occasionally going to come into play, even though we're about to leave it for a moment. Okay, so we have enough definitions now to introduce the polar coordinates. So I'll do another graph. Here we go. So now here's our complex plane. We have z equals x plus iy. And I can introduce, I'll introduce a kind of a line segment to this point. I can introduce the magnitude, which I'm going to call r, and this angle theta. So now we have x and iy. So yeah, we've seen polar coordinates before, and now we're just doing them with the complex numbers here. So we can say z, in this case, the real part of z is equal to x, which is r cos theta. Imaginary part of z is equal to y, equal to r sine theta. And of course, I could, instead of r, I could write magnitude of z if we want. Okay, that's all implied right here. Okay, so far so good. Now, if we were going to multiply these together, you know, a z1 and a z2, seems like we'd be running into the same problems we had up above. But now this amazing identity comes into play due to Euler, and that is the following. That is that e to the I theta is equal to cosine of theta plus I sine of theta. We're talking about numbers here, cosine and sine. So apparently, if we're talking about a number z, it's where r is equal to 1. So that would be talking about the unit circle. But this relation here is going to make things really convenient. Let's draw a unit circle once again. So if we have z magnitude equals 1, then we're looking at the unit circle. If that's the case, otherwise, you know, generally r cosine theta. Okay, so how do we prove this? Well, we're going to prove it using the series expansion of the exponential and the cosine and the sine. And I'm going to start it off, and you guys will complete this for homework. So the proof, after all, we know that e to the I theta is just the exponential function, so let's just treat I times theta as a normal number and fit it right into our definition of the exponential. So I theta to the k over k factorial, k equals 0 to infinity, right? This e to the x would have been x to the k factorial, k goes 0 to infinity. And let's just do a few of these. So for k equals 0, we just have 1. Okay. For k equals 1, we have I theta, and that's it. For k equals 2, we have I squared theta squared over 2, because 2 factorial is 2. So we have I squared theta squared over 2, but I squared is negative 1. So minus theta squared over 2. Now we'll go to the third one, I cubed theta cubed over 3 factorial. Well, I cubed is I times I squared, so it's I times that negative 1 we just had. So it's minus I theta cubed over 3 factorial and then what? I to the 4th theta to the 4th over 4 factorial. I squared is minus 1. Another I squared is times minus 1. So minus 1 times minus 1 is plus 1. So we're going to have plus theta to the 4th over 4 factorial. Now if you keep going on this, and you don't have to go out to infinity by any means, you're going to see we have real and imaginary parts. So this series turns into 1 minus theta squared over 2 plus theta to the 4th over 4 factorial. I'm just going to write plus minus da da da. So that'll be our real part. And if we pull out this imaginary part here, we'll have theta minus theta cubed 3 factorial and so on. Okay. And what you'll see is when you expand out or look up, but you can actually just expand these out by the definition, that this is going to be your cosine and this is going to be I times your sine as you take it out to infinity. So the homework aspect of this is to complete this and make sure you really see it. Okay, I did several of these and the pattern's clear. You can do it with an induction or whatever is clear enough. Okay, so you need the cosine and the sine Taylor series, and they're well defined, so you can get those as well. Okay, so proof, homework, complete this. Okay. That's an exclamation point. There we go. Okay, so now we have something we can work with. This is utterly important. And by the way, the convergence behavior of the exponential is excellent. Okay, there's nothing to complain about with the exponential function here. In a complex variables class, they'll prove this type of thing a little more, but there's nothing to worry about. So, what we find now is that multiplication, division, roots, and things like that are very convenient. So now that we have Euler's formula, multiply z1 times z2, now we can say that's r1. Well, I'll go ahead and write the magnitudes for the moment. So that would be z1 magnitude e to the I theta 1 times z2 magnitude e to the I theta 2. Okay. So that's z1 z2, or r1 But look what we have here, e to the I theta 1 plus theta 2. And if we divide two numbers and divide z1 divided by z2, I'll use the letter r this time, so r1 e to the I theta 1 divided by r2 I theta 2 r1 over r2 theta 1 minus theta 2. So very easy, and we have a great visualization of these things up on the unit circle or on in the complex plane, because we're just adding those angles or subtracting them. How about the square root? So we would have z to the 1/2 power will be equal to r e to the I theta, the 1/2 power. So we'll have the square root of r. And as far as the angle goes, it's just e to the I theta over 2. So yeah, we can visualize all three of these examples here. Here we had we had adding the angles, subtracting the angles. In particular, actually, let me just look at this one here. So we want the square root of some number z here. There's the angle theta. We can see, especially it's simplest if you're on the unit circle, you don't have to worry about the length there. You're just on the half angle. So if that was theta, let's go ahead and draw both of them in. So if that was theta, then we would have theta over 2. So the square root would be here. If this were on the unit circle, the square root would be right there. Okay. So now we can do, what about the nth root? If we wanted the nth root, we would take the nth part of this angle, and the nth root would be somewhere right there. Square root, what about the nth root? The nth root, question mark. For what about the nth root of -1, for instance? Example. And this is going to be a homework, but I'm going to set it up again. We're going to find the nth root of -1. Find the nth root of -1. Square roots are easy, right? Nth root of -1 is a little more interesting. But it allows us to learn to visualize these things. Okay, so that's a good homework problem. Find the nth root of -1. Homework. But let's just explore this a bit. So here's -1. X and Y axes. We want to find the nth root of -1. First of all, what we can do is express -1 in terms of these polar coordinates. Because what is the angle now? We've been measuring our angles from the positive x-axis. So -1 has the angle pi. Okay. So -1 is equal to e to the I times pi. E to the I times pi. You can see I is equal to e to the I times pi over 2, interestingly, right? I'm just using our definition here, r e to the I theta, so we want the nth root of that. So for this expression here, we want a number which when we take it to the nth power, this was, by the way, this is an example right here. So we want a number, we take it to the nth power, so we need z to the n is equal to e to the I pi. So we're going to find one of these very easily. So z is equal to e to the I pi divided by n. And if you want to be concrete, you could maybe start with the n equals 4 or some smaller number. So e to the I pi over n, so if n is large, you'd be on your unit circle here and say this here is, suppose this angle is pi over n, then n of those multiply together, it just keeps going around until you get to e to the I pi. But here's the thing, this is one root, but there are n minus 1 more of them. But there are a total of n of these roots, and they're all placed along, somewhere along the unit circle, such that when you multiply them, when you take the n times that angle, it turns into pi. But they can be angles such that if you go around, you take n times that angle, and you go around a number of times, and then you land on pi. Okay, so the hint that I'm going to give here, hint, you're looking for n times theta equals, well, if I say too much, I'll give it all away. Okay. N times theta is equal to pi, except it's pi plus however many times you went around the circle. Okay. Question mark. So I'll leave that for you. I'll let you guys figure that out. I'll do an example of z to the 4th is equal to minus 1. So for n equals 4, and we'll go ahead and take our, got our unit circle here for orientation. So I'm going to do something to the 4th power. Apparently, if I take this pi over 4 times 4, right, I'll land right there. So that's one of those roots. Okay. So there are three more angles taken times 4. And you can think of yourself kind of ratcheting around the circle counterclockwise. So there's one of the roots, 1st, 2nd, 3rd, 4th power. Check. Okay. Now another one of those roots would be here. 1, 2, 3 of these, right? So 1, 2, 3, 1, 2, 3, 1, 2, 3. So this is another one of the roots. Okay. I'm gonna put these roots in blue. Okay. If you look at them and think about it, those are the 4 roots of -1. The 4 fourth roots of -1. Okay. So seeing what I did there, see if you can get the nth roots. Okay. So that's a fun little problem. And the idea of this multiplication and going around counterclockwise is also really important. I will consult the clock now. Okay. We're close to finishing for the day. Okay, having done all of these things, we'll have one more little example that'll take us to our harmonic oscillator differential equation, which is where we'll leave it. Remember, we wanted all this to be germane to the problem of linear differential equations. So these are just warm-ups to get used to these things right here. Now consider z of t is equal to some constant. I'll make this a real constant, e to the I omega t. Okay. Go straight to where we're doing. So that is to say, we now have theta is equal to omega times t. Well, since theta is an angle, omega is an angular frequency, and if you just want to look at this thing in the complex plane, okay, A is real for the time being. Okay. A is a real number. We've got our x and y, and basically we have a point when t is equal to 0, we're just out here at A. Okay. We have a point that is going counterclockwise, okay, because theta is just growing linearly in time, and theta was real, omega is real, time is real. So now we have something moving. This is just the motion of a dot here counterclockwise in the complex plane. Okay. So let's make a sentence out of this which describes a counterclockwise motion. With angular frequency omega. Now when we were talking about circular motion, we could have been talking about this, right? Theta is omega t, counterclockwise, takes us right back to our plane polar coordinates. But now it's with this complex function here in the complex plane, and let's do a derivative. dz dt. Well, remember, if we took the definition of the derivative, that would be limit of difference quotient, okay? And the difference quotients are just made using the laws of arithmetic, so we can just inherit the definition of the derivative right into here. Difference quotients, limit, all works well. Therefore, we have, with respect to time, we have a e to the I omega t because it's the exponential function, and then the inner derivative gives us times I omega. D squared z dt squared is going to do the same thing again. We've got the I omega. We've got the derivative of a e to the I omega t once again, which is going to bring another I omega. So I omega squared a e to the I omega t. Or, since this is the original number z in the first place, we have d squared z dt squared is equal to minus omega squared z, which is our linear differential equation with constant coefficients, except now with the complex number instead of a real number. So apparently this is the general solution to our basic differential equation of harmonic oscillations. So that's where we arrived at today. We'll pick up with this next time. So have a good look at everything we did with the complex numbers. All of these definitions come into play throughout the rest of the semester, and in particular, by landing on Euler's formula, we were able to get our differential equation of the harmonic oscillator right here. And that means that is a solution. Good. See you guys next time.